Alright, hello everybody. So today's lesson we are investigating the sine function. So sinusoidal functions, like other periodic functions, repeat at regular intervals. Okay, so remember from last lesson we were talking about periodic functions like your heartbeat and stuff like that. Things that happen at regular intervals. Unlike other periodic functions, sinusoidal functions form, I'm going to highlight this, smooth symmetrical waves, okay? In the previous lessons, things could have been periodic, but they weren't necessarily symmetrical, right? So the symmetrical is the key part here. That's what makes a sinusoidal function. Such that any portion of a wave can be horizontally translated onto another portion of the curve. We'll talk about that after. And then the sinusoidal functions are formed from the transformation of the functions y equals sine x and y equals cosine x, okay? So these are your trig ratios. And in this first example, all right, investigating the graph of sine x, what we are doing is we are taking degrees, okay? So like this x right here, that is in our previous trigonometric unit, right? Like that's your angle, that's your theta. So like think of this x here as theta. And what you are doing is you are calculating values of y, right? Because it's y equals, and you are taking the sine ratio, and you're just taking values of theta, so angles, ranging from 0 all the way to 360. Okay, so if you were to do this for every single angle between 0 degrees and 360, like 1 degree, 2 degree, 3 degree, and get your corresponding y's, like a table of values, right? So like x and y, and we have a table of value right below us, but I'm just trying to show it in a different way, something you're more used to seeing. So if you take literally every value, 1 degree, 2 degree, dot, 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 all the way to 360 degrees, and you calculate what the value of sine is, right? And then you take these, remember these would be ordered pairs, and you plot them on a graph, what would that graph look like? So let's explore, okay? So right now in this problem, these are all our degrees. So it literally says degrees right here. So these are degrees that you are just taking your calculator and solving, okay? So when I get this input right here, what I am doing is I'm saying, okay, well, what is the value of sine 90 degrees? And if you put that on your calculator, you'll find that value to be a value of just 1. Just 1. There's no units or anything. It's just the value of 1. Okay, well, do it again for sine 120. So you just take sine 120 degrees, hit equals, and on my calculator, if I just round it, I'm going to get 0.9. And do that again for here. You're taking sine of 150. Okay, so this is whole function idea, like, and that's why I'm taking this slow right now, is I really want you to understand that all of these values right here are just the outputs of you saying, okay, well, what was the value of sine at that angle? And you know what, let's do this sine 150. I'll finish there for a second. 0.5, if I do that. Actually, I'll do one more. 8. So let's plot so far what we have, okay? So everything here, like these are ordered pairs, right? So like what this corresponds to, what this plot is, I mean, it says it right here. So these are this would be the coordinate 0, 0. This one would be the coordinate 30, 0.5, and so on and so on, okay? So if I'm plotting the first one, 0, 0, well, this would be 0, 0 right here. Okay, the next one is 30 and 0.5. So 30, 0.5. The next one over is 60 and 0.9. So 60 and 0.9, that would be right here. And then I have 90 and 1. So I'm just literally reading what I have in that chart up top, and I'm just putting them in their ordered pairs, okay? So I find that the disconnect happens is people forget what they're actually plotting. And what you are plotting right now, these are degrees, like these units right here. Sorry. This axis right here is degrees. And all of the numbers you see over here, from here all the way down, these are what the value of sine x is, okay? So that's a horrible line. Let me draw that better. So this axis represents sine x. So what you were doing is, if we connect these dots right here, right, like any other function that we've done, if I connect these dots, okay. So there is half of my curve, right? Because I haven't done these other half right here. But again, I'm just going to take this slow because it's the hardest part about understanding this, is what you are finding right now are, if I was to say, okay, well, right here, this point right here, well, that's like halfway between 30 and 60, so that's 45. So if I was to take the sine of 45 degrees, what number would I get, right? Well, you have a graph right now as it stands that says, oh, well, your degrees, so the value I'm choosing, 45, on the y-axis are all your outputs. So if I just went right across, like here, well, I would see that's a value of maybe like 0.7. So sine of 45 is 0.7. That is your ratio that you are getting when you take the sine of 45. So if you do that for every single number from 0 to 360, okay, and I mean, I'm not going to go into the unit circle, but why do we stop at 360? If you think about what's happening, you're going from 0 degrees and you're traveling in a circle, and you know, when you were a kid and you jumped on a trampoline, you said, oh look, I just did a 180. You know, if you did a complete revolution and you ended up back where you started, you would have traveled 360 degrees and you would have came right back. So that's why we stop at 360, because you're essentially saying, oh, what happens as a triangle is drawn all the way from 0 to 360 degrees, right? My triangles are horrible there, but you get the idea. So let's finish up our table here. If you do the sine of 210, you know, just literally take a calculator, say sine of 210, you'll get 0 negative, okay? Notice how we're getting negative answers now. Then you take the sine of 240, you're going to get negative 0.9. Take the sine of 270, you'll get negative 1, negative 0.9 here, negative 0.5, and then you'll be back to 0, okay? And you can kind of see like this pattern forming. Look how all the numbers are similar. There is a symmetrical pattern that is occurring here. But let's finish up our graphs. The last point we plotted was this one, the 180 and 0. So let's keep going. Next one is 210 degrees. So 210 degrees is right here. And then negative 0.5. So 210, negative 0.5. That puts us right here. 240 and 0.9. That's right here. 270 and negative 1. That's right there. 300 and negative 0.9. 330 and negative 0.5. And then 360 back here. Okay. There we go. Let's see if I can just draw my curve smooth. Perfect. And if you're like, oh, does it stop here at 360? Well, ask yourself, can I take the sine of 390 degrees? Yes, you can. And you'll get a number that is 0.5. So you'd actually be right up here. I'm going to draw this in a different color though. That'll make sense in a second. But this would keep going. It would just keep going, and if you kept doing this, you know, you kept putting numbers bigger and bigger and bigger, you would just keep getting a curve. All right. So let's look at this graph, okay? And so what you have just graphed here, by the way, proper communication, you've graphed y equals sine x, okay? You have chosen values for x going from 0 degrees all the way to 360 degrees, right? And then you've plotted the y values, the ratios, the outputs, right? Like remember back to our trick. The output of a sine ratio gives you a ratio, like ratio of opposite over hypotenuse. So state the following for sine x with no restrictions. So period. How long does it take us to get back to where we started? Well, if we think about what this sine graph looks like, it's starting to go upwards at the beginning, right? And then it reaches its peak right here, and then it starts to go down. So you might be saying, oh, okay, well, like, I see it's going upwards right here. No, like these are not the same parts right here, right? Like here you have a max, here you have a min. So then when does the graph start right back up? Well, it starts right here in this yellow part. This is when it starts to do this. So that yellow part that's right there, that is equivalent to this beginning part right here. They are just one full period away from each other. So the period is how long does it take you to go from here all the way to here? Well, you just read off. If this is the x-axis, if this is 0 degrees, and this is 360 degrees, well, from 0 all the way to 360, you've traveled 360 degrees. Okay, x-intercepts. Well, let's look. X-intercepts, there is one here, and one here. So those are occurring at 0 degrees, 180 degrees, and 360 degrees. Where does the y-intercept occur? The y-intercept is right here. So that happens at what value? Well, it's a y-intercept, so you're not giving it values of degrees, you're giving it ratios, right? You're giving it what value of sine x is it at the intercept. So in this case, it's going right through the origin, so it's just 0. What is the max value of y? Well, this red dot I have right here, there's your maximum. You read that across, well, there you go. It is a value of 1. And do the same thing for the minimum. Here's your minimum, and you just read that across. Oops, sorry, that's a bad line. It should be right on this. There you go. And that should be a value of -1. There's your min. Your min. That was your max. And then what is the amplitude? So, recap from yesterday. The amplitude is the distance from the center line, all right, all the way to either the max or the min. Or it's max minus min divided by 2. So, you can visually see it. It's like this is the center line right here. And how far would you have to go to get up top there? Well, that's a unit of 1. Same thing here. How far would you have to go down to go here? Well, that'd be also 1, right? But let's mathematically show it. Max minus min over 2. So that is 1 minus -1 over 2, giving us 2 over 2, or 1. State the coordinates of 5 key points that would allow you to draw the sinusoidal function of y equals x quickly over the interval 0 degrees and 360. Okay, please commit these to memory, all right? These 5 key points, all right? The 5 key points are where the numbers are either 0 or 1, or like 1, right? Like, or -1. So if we look at that, our 5 key points are coming from right here. There is one of them. Here's another one. Here's another one. Another one. And another one, okay? So your 5 key points are when you have intercepts or your max or your min, okay? So they are the x-intercepts and your max slash your min, right? So we have 3 points, and then we have 2 points, and giving us a total of our 5 points. So, and commit these to memory, okay? And as long as you do more graphing, it won't be so bad. You'll start to memorize them, but at the beginning, you gotta just memorize. So, remember, we are plotting them at, like, the points I'm giving you are values of x, and you're giving values of sine x as your y coordinate, right? So these are the degrees, right? Degrees. And these are your outputs, your ratios. So the 5 key points then, if I was to give it to you in that format, well, the first one is 0 degrees and 0. So 0 degrees, 0. And then your max occurs at a value of 90 degrees and a value of 1. You have your next intercept at 180 degrees, and that has an output of 0. And then you have your other one that's at 270 degrees, and that's giving you your minimum, minus 1. And then you have your last point, 360 degrees. Finally, back to your x-intercept, 0. Okay, so commit these 5 points to memory. Okay, stating the domain and range for y equals sine x. So remember, the range is talking about this value. The range is dealing with the y's. The domain is dealing with the x's. So when you say domain, what you're saying is, okay, is there a degree? Like, is there some degree that I cannot take the sine of? That is not possible. And, you know, you might be inclined to say, oh, well, this graph right here doesn't go below 0. But check for yourself. See, are you able to take the sine of a negative number, like let's say negative 30? What do you get? And try it out for your calculator. And what you'll find is that there is actually no point where you cannot take the sine of. So this is actually x belongs to real numbers. You'll just, any number will work. You can just take the sine of any degree, however big or however small. So our range, on the other hand, you can clearly see that whenever you use the words maximum or minimum, that literally means that is the highest point or the lowest point you'll ever hit. So there is a constraint on your y's. Your y's are constrained between your minimum, which is negative 1, y, and it also has to fall between 1. So you read this as saying, well, this is your minimum, and this is your maximum. The y values can be any number in between. And visually, that makes sense. Look, they can be any number in between your highest point and your lowest point right here. They'll just always kind of fluctuate and oscillate. That's a term commonly used, oscillating. They'll oscillate between your max and your min. Okay, so example 1. Which of the following situations represents a sinusoidal function? Justify your decision. So in the beginning of the lesson, I'm just going to scroll back up. In the beginning of the lesson, I highlighted the smooth, symmetrical waves here, okay? So visually, you might say, oh, okay, well, I'm going to jump ahead to B, but you might say, oh, well, this is periodic right here. I can see I have this pattern repeating right here. And it would start right here, right? Like you'd have the whole pattern starting again there. But notice that this is not symmetrical, right? Like if I was to put a line right through it, you're not going to see the same thing on top and bottom, right? Like you're not symmetrical top and bottom. And it's not smooth. You have all these jagged edges here. That's another part, smooth and symmetrical. So when you look at A, well, this is a smooth curve. This is a smooth curve like this. So this is symmetrical and smooth. So this is sinusoidal. Sinusoidal. Right? Justify your decision. Well, it's both smooth, and symmetrical. Right? You can see what I mean by smooth is like, oh, it looks like a bunch of parabolas kind of put together, right? And like you have this like center line here, and I can, if I was to take a cut right here, right? Like if I was to cut this right here, I could take that and overlay it right on top of this one, and it would be identical. They would stack right on top of each other because they're symmetrical. But in contrast, this one is not smooth. Not smooth. So not sinusoidal. And then if we look at this one, it looks smooth, right? Like you can see, oh, I have a bunch of these parabolas like this, but notice how over time your maximums are increasing. So you're getting higher and higher as you go down, and same at the bottom here. You're getting lower and lower as time goes on. So in this case right here, this is not symmetrical. Therefore, not sinusoidal. Therefore, not sinusoidal. Sorry, I should have added that here. Soidal. Okay. Example 2. Sarah is sitting in an inner tube in a wave pool. The depth of the water below her in terms of the time can be represented by the graph shown. What is the period of the function? What does the period mean in the context? Okay, so, Sarah's height above the swimming pool, like you have like one of these wave pools, right? So she'd be like in the pool, you have a pool like this, there's a bunch of water and the wave comes like this. And so Sarah at one point in time will be super high above the water, inner tube, that's her. And then like if you were to take a snapshot, maybe like a few seconds later, same swimming pool, but now the waves have gone down, so she's like down here now, right? So like over time with the waves coming, she's going to be going up and down, right? So that's what this graph, as time goes up, she's going up and she's going down. So we need to figure out, okay, well, this is a sinusoidal pattern. Like it looks identical to what we were graphing before. So let's find when the pattern repeats itself, because when you find when the pattern repeats itself, however long it took you to get to the start of the new pattern, that's your period. So in this, like the easiest place to find the periods are always looking at the peaks or the troughs, right? But in this particular problem, because the troughs and the peaks do not necessarily line up exactly on clean numbers, let's look for where the pattern repeats but on a nice clean number. So I'm going to start right here, okay? So what I am looking for is I'm looking for halfway between my max and my min. So, you might be thinking, okay, well, that's right here. But no, because right there, you're starting to go downwards, right? But at the start of my period here, I'm going up. So I need to find another point, which would be right here now, right? Same height, right? Because that's what a period, you want to find the same y value. And then notice how I'm going up and I'm hitting my maximum. So my pattern is going from this green dot I've drawn all the way here and to this point right here, right? I could have also done it from right here too. I could have also done from right here, gone up, down, and then gone to this one, right? It doesn't matter. It doesn't matter where you decide, as long as you're going from the same point to the same point. So actually, why not? Let's just use this one. It makes our life easy. The second one I drew. Well, how long did that take? How long does it take to go from here all the way to here? This is one period. Well, let's look on the graph. That corresponds to starting at 0 seconds and you travel 3 seconds to repeat your pattern. So the period equals 3 seconds. And what does this mean in the context? Well, what it means is that it takes her 3 seconds. So let's use my picture here, right? Like time is ticking along here. Time is going forward. But then you'd have one more scenario. Let me just literally copy what I have here, make my life easy. Copy. Paste item. It takes 3 seconds to go from her height. She goes down and then she comes right back up. This whole thing takes 3 seconds. 3 seconds to occur, right? Because it's just a pattern. So from this point, she would go down again and then come back up. And she'd go down again and then come back up, assuming that the machines never break down. So the period is 3 seconds. What does it mean in the context problem? I just explained it, but I'll put it in words for you. What does the period mean in the context? It takes 3 seconds to go from the max to the max, or min to min. Again, doesn't matter, right? As long as you're choosing the same point. So I didn't even use min when I found my period. I found the halfway point, but I went from same halfway point to same halfway point. That's one period. What is the equation of the axis? What does this represent in the problem? So remember, your axis is calculated by taking your max, adding it to your min, and dividing it by 2. So let's just look at our graph and say, what is our maximum? Well, our maximum, if each one of these ticks right here, so there's like a spacing of 2 represents a distance of 0.4. So our maximum then would be at 2.4. So we have 2.4 plus, and what is our minimum? 1.6. Divide that by 2. So let's see if my mental math is good today. That's 4, that's 2. So our axis of symmetry is 2. And that is a y value, because all of these inputs here, these are y inputs, right? I'm just reading them off the y-axis. So what units would the y-axis be? Well, that is 2 meters. And so what does that 2 meters represent? Well, in the context of our problem, let me see if I could draw my pool again. If she's at her highest point right here in her inner tube, and then, she goes down to the lowest point right here, so there's a time where she's up here, and there's a time where she's down here. Well, what the axis represents, it's the halfway point between those. So it'd be like when she's floating right here, when she is right here. And that halfway point, in what we just calculated, that is 2 meters, okay? So what does it represent in the context of this problem? What does it represent? I'll just answer that right here. It is the halfway distance between max and min. So she floats 2 meters above. Okay, what is the amplitude? So our amplitude, calculated very similar. So our amplitude, oh, by the way, I misspoke before. I called this a value of C. In this course, we're going to call it a value of D. So the axis is D. And, just for the sake of always writing, we can call this one just A. So amplitude is max minus min divided by 2. All right, so we have those values already. The max is 2.4 minus 1.6. Divide that by 2. Was that 0.8 up top? So that is 0.8 up top. Divide that by 2. 0.4. Okay. So what does that represent? Well, that 0.4, once again, is a meter, because all your inputs here are y's, right? It is the distance from your max to your min. So if I copy my picture that I've drawn right here, I just copy this picture, that 0.4 is saying, well, how far is it from my halfway point to my minimum? That'd be 0.4. Or my halfway point to my maximum. That would be 0.4. So in the context of this problem, it's 0.4. It is 0.4 meters from the axis to either the max or min. So approximately how high is Sarah at 11 seconds? Okay, so let's look at our graph and see where 11 seconds is. And approximately. So when I see that, it means we're not going to get a nice answer. We're probably going to just have to estimate. So if I look at my graph up here, okay, so our max value is 8, right? So yeah, we are definitely going to have to kind of extrapolate here. So if each one of these two squares represents a time, right? So that means this would be 9, and you'd have another 2 squares that would go by, and that would give you 10. And you'd have another 2 squares that would go by, and you would get 11, right? So really, we are actually 3 seconds. We are 3 seconds away from the point that we need to extrapolate. Well, 3 seconds, that seems familiar. Like, that's a very important thing. That is our period. So what that means is saying, oh, well, if I can just look at 8, wherever 8 is, so 8 is right here. So let's zoom in on that. That's 8. Okay, and what value does that give us? That gives us a value. My line's not super straight, but that gives us a value of, looks like 1 point, I don't know, let's call it 1.7. Let's say at a value of 8 seconds, at 8 seconds, you're at 1.7 meters. So if a period represents when you get right back to that starting, wherever you're starting from, you're getting back to the exact same point, that means at 11 seconds, you're 1 full period away from 8 seconds, you will be at 1.7 meters. So you are 3 seconds or 1 period from 8 seconds. Therefore, 1.7 meters high. Okay, last example. I know this is a longer lesson, but it's really important you understand the concepts here moving forward, okay? So please take time, watch it, go over it again if you need to, if you're confused. Example 3. Sketch the graph of the sinusoidal function with a period. So whenever you see sinusoidal function, you know, generally speaking, your graph is going to have to look something like this. It might be upside down eventually, but it's going to be smooth and symmetrical. So sketch the graph of a sinusoidal function with a period of 30, okay, an amplitude of 5, and an equation of the axis at 3.5. So I always find it best to start with this, okay? So let me put some numbers. Start with this. And then I think it's easiest to go do this one after. Figure out where you're going between, and then we can deal with this amplitude of 5, okay? Deal with this last. I mean, these are kind of interchangeable. But start with the axis. So the axis at 3.5. So that means right here, if this is 4 and this is 3, that means you have a line and you draw a axis of symmetry as a dotted line, very similar to like what we did in the quadratic unit, where this right here is your axis of symmetry, because it's not actually a line on the graph, right? It's just a fake floating line that splits the graph in half. So there is your graph, and you label it as y equals 3.5, okay? Now we have a period of 30. So what that means is that if we start at 0, okay, I could have chosen anywhere. That means I need to finish my graph at 30. So between these 2 points right here, I need to have this shape. It's a sinusoidal function. So I need to go both to a maximum, I need to go to a minimum, and I need to get back to where I start, right? So these are the 2 points. I need to see a max, I need to see a min, and then I need to get back to my start. So how many squares do we have here? If we think about this graph being in two chunks right here, you have half your graph representing the max part, and then you have the other half of your graph representing the min, where it goes down, right? So if we have 4 squares right here, well, we can kind of see, well, our halfway point is going to be, 4, so, oh, sorry, we have 1, 2, 3 spots. Halfway point is going to be somewhere in this region right here. Well, exactly in that region. It's going to be halfway between your max and min. So you should see this 0, this yellow dot right here will cut your graph in half like that. That's why I think starting with a period is the next best option. So you can see then your graph will have a maximum in this region and a minimum in this region. We'll now talk about the amplitude. The amplitude says you're going to go 5 up from your axis. So our amplitude is 5 up from this point right here. So 3.5 plus 5 gives you 8.5. Oh, 8.5. So 8.5 is right here. That's 8.5. So that means halfway between these points right here, I'm going to go up from my starting point, hit my maximum, and then hit the point that splits the graph in half. And then I'll be going 8.5 down from this point. So going 5 units down from this point. So what is 3.5? 3.5 minus 5? Well, that's going to give us negative 1.5. So negative 1.5 would actually put you right here. There is negative 1.5. So my arrow's slightly off. I'll just redraw that. So we're right here. So that means we go from our halfway point, we hit our minimum, and then we go back up to our starting. And there you go. That is you graphing a sinusoidal function. You have your max, you have your min, you have your axis, right? And you've done the correct amplitude. So there is our homework. Please, please do it. I'll see you in class. Bye for now.